So here, Notebook 10 is on multiple dispatch, and it is the design paradigm of Julia. So it's what makes Julia, so generic and so fast. So to talk about multiple dispatch, we're going to start by talking about some things that we've already seen. So we've already seen that we can declare a function f, for example, and that we don't need to specify, what f takes when it squares things. Julia figures out on its own that f is perfectly capable of squaring integers and matrices and strings to concatenate them together. But it also figures out on its own that that f does not work on vectors because there isn't a well-defined way to multiply vectors by one another in Julia, or more generally in math. And so Julia figures this out for us. Now, if we wanted to, we do have the option in Julia to specify the types of our input arguments. And so that's what I'm doing in this example here when I declare a function called foo. This is not it's not at all a meaningful name. It's just some random function. The point is that I'm declaring some function that does something, and it takes particular types. In this example, foo is taking two strings, and it's going to print, when it gets called, that my inputs x and y are both strings. Now, we know that it's taking two strings because of the annotation here. So if I want a given input argument to be of a certain type, I'll follow the name of that input argument in the function declaration by 2 colons here, and then the name of the concrete or the abstract type that I want that input to be. So here I'm saying x : string for x is a string, and also y is a string. When I declare this, foo now exists, and I can call this function foo on 2 strings, for example, hello and hi, and that works the way that we might expect it to. Now, if I call foo on 3 and 4, it doesn't work. And the reason it doesn't work is that I didn't write foo in a way where it should work. There's no way to call foo on 2 integers because foo only accepts strings the way that I defined it. Now, if I want foo to start working on integers, I can write foo such that it does. And I can do that by saying, okay, well, now I want x to be an integer and I want y to be an integer. This is my new foo. And when this foo gets called, I want you to print that both x and y are integers, as they are constrained to be. So now when I call foo on 3 and 4, I'm getting this now expected output, my x and y are both integers. So we know that this foo is being called when I call foo on 3 and 4. So where this starts to get interesting, and where we start to get a hint of what multiple dispatch is and what it's doing, is that when I call foo on hello and hi, these 2 strings, I'm still getting this output that x and y are both strings. And the reason is that when I wrote foo here, when I wrote this definition for foo that takes 2 inputs, x and y, I didn't replace my original definition for foo up here. I didn't overwrite this definition. What I did was I added a second definition, and in Julia that's perfectly fine. I can write many, many, many different definitions or implementations with, for one function name. And so the idea, behind a multiple dispatch is that, or one of the key concepts there is that we have a distinction between generic functions and methods. So generic functions are sort of, we can think of those as sort of the abstract ideas that we have tied to particular operations. So what I mean by that is that, we in our minds might have an idea of what it means to add things together or what it means to subtract things. And when I, as a human, am thinking about adding 2 things together, I'm not thinking about using different algorithms for adding together floating points versus integers. I do those in very similar ways. But on a computer, we need specific implementations for adding together strings or adding together int64s or int32s because of the way that those numbers or generally those values are stored or represented on a computer. And so, we as the users might want to just think about these sort of general ideas like addition and multiplication, whereas a computer needs, again, these specific implementations for specific types. Now, generic functions are sort of these general, more loosely defined ideas associated with operations, and methods are these specific implementations for particular types. I thought I had something to add there, but I'll come back to it if I remember. Um, so the idea is that we as the user in Julia can work with these more generic function types. We can just use functions like foo, or we can add things together, and we don't have to specify, what types we're going to be adding together in advance of calling addition. Julia is going to figure that out for us by relying on built-in functionality that has specific implementations for all of these lower level operations that have already been well optimized for particular data types. So one way that we can see how many different methods exist for a given function is by using this methods function. So if I call methods on the function foo, we can see that there are two different methods for foo sitting around. One is for foo that works on two integers, and one is for foo that works on two strings. Similarly, if I were to call methods on the plus operator, we see that in Julia there are 163 different ways to add things together. So this is basically a combinatorics problem where we have, adding big floats to big floats, and how do we add dates to other dates, and complex numbers to complex numbers, reals to complex, and what have you. So another really useful function when we're starting to think about multiple dispatch is, how do we actually tell what version of a given function is being dispatched? And for that we can use this @which macro. So this @which macro we saw before in Notebook 9. What it's going to do is it's going to tell us which version of this foo function, which method associated with the function foo, is actually being sent out when I call foo on these particular input arguments. So when I call foo with 3 and 4, we see that the version that's being dispatched is in64. We don't need to have a particular return type to see which version got used. Similarly, if I call @which on 3.0 and 3.0 here, we see that the version of addition that's being called under the hood is the version that works for float 64s. So I guess one of the key ideas here is that there's this traditional understanding that there is a necessary trade-off between the speed of lower level languages and the ease of use of higher level languages. But what's going on here is that we've really gotten the best of both worlds, and the way that we were able to do that is that we've taken advantage of the fact that the way that lower level languages, or languages that generate more efficient machine code, get so fast is that they're able to make use of additional information. If we're coding in C or if we're coding in Fortran, we tell the compiler up front, like, this is an integer, or like, this is a float, and then the compiler can use that information to apply constraints that allow it to perform optimizations that that we luckily don't have to do. When we're working in a language like Python or MATLAB, we aren't able to communicate with the compiler in that way, or the interpreter. We're not able to say, this is an integer, therefore do things really fast for integers. But in Julia, we've sort of abstracted away that part where we provide that additional information to the compiler, so the compiler can take advantage of type information because of this design paradigm, multiple dispatch. It has the advantage of taking that information into account, but we as the user don't have to specify it, because we can just work with these generic functions that allow us to work with these more abstract ideas and not worry about those lower level implementation details. So with that, I did mention earlier very briefly this notion of a type hierarchy in Julia, where I said that at the very top of our tree we have this notion of an abstract, an any type that encompasses all concrete types, and then these concrete types at the bottom with other abstract types in between, in the middle layers, like number, for example. So this number abstract type includes all integers and floating point numbers. So in this next example, when I say that x and y are both going to be number inputs, and then I'm going to print accordingly that x and y are both numbers, I now have created a way for foo to work on any number for which a method hasn't previously been specified. So if I call foo on 3.0 and 4.0, I'm getting this method declared for numbers being called. If I went back to foo being called on just 3 and 4, we're still going to go to the most specific implementation, the version that was already written for integers, rather than using the general number version. And finally, we can always declare functions in a way where we've provided a fallback or a more generic use case. So for example, here I'm declaring foo without specifying what x and y are, and now when I call foo on a vector, I'm going to get an output that that calls this function. So that's our very much whirlwind tour of multiple dispatch. And